Hi, everyone. Thanks for coming to my talk. This is a developer conference, so it's about things that don't work yet. And I just want to make that clear. So there's some ideas here, and I'm also going to be talking about work done by a lot of different people. A little bit by me, but a lot by other people, just to make that clear as well. Okay, so I'll start with some basic concepts and background. So Postgres is really old. And it began in 1985. And there's a paper called The Implementation of Postgres by Stonebraker and crew that was written in 1990s. So that the project was only 5 years old. But it was still 5 years before POSIX standardized Threads APIs. And Windows didn't exist. Windows with Threads didn't exist yet. That was 1993. At that time, in the late 80s and early 90s, there were, I guess I should say late 80s, some of the high-end Unix systems did have Threads, but they were all incompatible. And so in that paper, they just, they mentioned that they planned to essentially rebuild Postgres using Threads at some point when they could. And they started with a simple process model, which we still have today. So we essentially haven't done what the project plan said we should do. One of the interesting systems they had was the secret symmetry, which is mentioned there. I think they did a lot of their work on Sun 4s, but they also had the secret symmetry system, which had a huge number of CPUs in a big box. Finally, in 2011, the C standard introduced a standard way to do threads. And I'll look at some of these things a little bit later. So that's kind of the beginning that I wanted to start with. And with a bit of background on what a multi-process design looks like. So there's essentially three different reasons you might want to start a new thread of execution. And Unix traditionally used fork. It was the only way to create a separate thread of execution. So the first category I'm talking about here is if you want to create a multi-process system like Postgres, you use the fork operation. Windows doesn't have that. And we'll look in a moment about what consequence that has for us. The second thing you might want to do is run a different program, start up a different executable as a sub-process. And on Unix systems, you do that with fork or vfork. I'll talk about that in a moment. Or POSIX spawn, which almost no one uses. Windows has a create process function. It can only create a new process running a different executable. Or it could be the same executable, but it won't share anything with the parent. And the third thing you might want to do is start a thread in the current process. So that's it's a new thread of execution, but there's no new process. It's running inside the same process. And I'll look at what that actually means in a moment. And Windows has that third option. So Windows has 2 and 3, but it doesn't have 1. And yet Postgres is built essentially on 1. So one question is, how on earth does that work? While looking into the history of this stuff, I found this paper really interesting. It's not that old. It's 2019. It describes how fork was, in the beginning of Unix. It wasn't actually original. Other operating systems of the time had a fork, but they had much more sophisticated forks that could control many more things about the newly created thread of execution, including the memory map and other things like that. It's a very simple looking interface, but according to these operating system researchers, it's essentially transferred an enormous amount of complexity and problems to other parts or essentially to the application developer. And you can see that all kinds of systems invented variants like vfork, rfork, and clone from Linux, and rforks from Plan 9, and vforks from BSD and became part of POSIX. And I'll talk about what those things do in a moment. These researchers say that essentially all new systems should have only 2 and 3, and 1 was really like an attractive and simple idea that turns out to be a little bit painful. So when I say 1, I mean plain fork. I think, yeah, I'm not sure that everyone agrees with this take, by the way, but it seems to be a fairly influential paper on the topic, and it certainly gives a lot of interesting background if you want to read something about that. So looking at fork, pretty sure everyone knows how this works, but I'm just going to super quickly go over the memory map stuff. So fork creates a new process which is just like the parent. You call fork, and it returns twice. Once in the calling process that we now call the parent, and then once in the child process. And you have to check the return value of fork to find out if you are the child or the parent. You've essentially been photocopied. And that forking operation copies all of the private mappings in the memory map of the parent. And I've got an asterisk there because it doesn't really copy it, but conceptually it copies the private mappings. So that includes the code, shared libraries that are mapped in, the executable itself, the global variables that that go with all the libraries and executable and so on. The stack, the call stack of the calling thread, the heap, everything, all the private mappings. The shared mappings, that includes shared memory that was set up explicitly using mmap or maybe the old System 5 shared memory system calls. Those, on the other hand, do not get copied. So I'm showing the parent in orange or yellow, whatever that is, and the child in blue. And this shared memory here, I've got a line connecting them because if the child modifies that memory, the parent will see the modification and vice versa. It's the same virtual memory object mapped in two different places, whereas the private mappings above, the executable and so on, conceptually they're completely separate copies, although systems don't actually waste memory on copies. We'll talk about that in a moment. But fork also has, to understand it and use it safely, you have to see how it works, like how it affects all kinds of other resources or properties of a process. So if you look at the POSIX documentation for fork, I think it's got about 26 bullet points and how it interacts with all kinds of different things like signal masks and other things like that. So there's a lot of complexity there to actually use it correctly. And we've been tweaking that stuff for years in Postgres, and it's really old because which things get sort of inherited and which things it's bad to inherit and so on. You have to control that stuff in different places, whereas the alternatives were complex in a different way. So like create process on Windows, I think it has about 10 arguments or something, and it's got all kinds of flags, which you look at it and you think, well, fork is such a beautiful, simple thing. Why don't we just use that? But the complexity is still there. It's just scattered all over the place, and everyone has to learn about it and get it wrong lots. So copy, I put an asterisk on copy. The VAX, which appeared in David DeWitt's amazing talk just before, that machine brought virtual memory concepts as we know them to mini computers. I think all of the ideas were present in like way more expensive mainframe systems, probably quite a long time before that. I don't know too much about those systems, but this was the arrival of virtualization of memory in hardware that could, in these mini computer systems that didn't cost millions and millions of dollars. That in the 80s, both main strains of Unix, the BSD Unix systems, and the AT&T systems, they used VAXs to sort of rebuild to build virtual memory systems on top, and that kind of design, the way that works, influenced the even cheaper computers that followed, including the i386 and 68,000 chips with MMUs and so on. So that hardware allowed the kernel to implement copy on write, so that the child process doesn't actually, the earlier PDP Unixes would literally copy the entire process memory. They didn't even call it a memory map, I don't think. I think it was just like, here's this chunk of memory. But then those systems probably had something like eight memory pages in total or something like that. So it wasn't too bad, just because their programs weren't huge. But the VAX hardware allowed them to perform copy on write. So it became a lot faster. But the page table, which is a data structure that has entries for every single page of memory that's in the memory map, that still has to be copied in most operating systems. It's not technically necessary. They could implement something that shares page tables. And you can see that in some operating systems like Solaris. Linux, huge pages do share the page table. I don't understand the stuff well enough to comment on it myself, but I have seen some experts saying that it doesn't work as well as it could. And there is ongoing work to make regular page sizes, page tables be shared on Linux. Then again, people have been trying to do that for over 20 years. I think there are about 4 different attempts with patches that didn't eventually make it in. The current group of people that are working on that are based at Oracle. I don't know that much about that myself. I would assume that Oracle wants that for the same reason that we would want that, because they do a lot of forking. And forking, when you've got a huge memory map consisting of a very large number of pages, it just has to take time, and it also has to occupy a lot of memory. So that's a lot of duplication. So what do we do on Windows if we don't have fork, and yet Postgres is built around fork? It's kind of a miracle of engineering, if you ask me, that Postgres has been made to work on Windows like this. It does. There's many things to look at and think, well, like, it seems kind of crazy, but it actually works, and people are running this in production, and it's really just a tiny emulation of the simplest things that you need for Postgres. It's certainly not a general emulation of fork. So I said before that Windows can only create a process with the create process function. That means that it inherits handles, so things like sockets and certain types of things can be inherited, and you can control that. But the memory map is certainly not. It's just completely replaced. So it's similar to the previous slide showing fork on Unix, but here I'm showing that I've tried to capture that the executable and the heap and so on might be at a different address, so I've kind of shifted them on the picture, if you see what I mean. It's also really slow. And we need to have, in Postgres, we need the main shared memory segment to be in the same place. So we try and map it in the same place. I don't fully understand that code, to be honest, but it seems to be prepared to sleep and retry. So I think I don't have the details in my head right at the moment, but basically we arranged for just that one piece of memory to be at the same address, which I think involves fighting against address space randomization stuff. I know that scheme adds at least 40 milliseconds to a trivial parallel query just because it's so hard to start up a process to simulate fork in that way. Probably it's much worse on a serious size system. I'm not a Windows user, so I've never really looked into this. I've just studied problem reports, and that's the smallest number I've ever seen anyone report for how slow, a select one in a parallel worker, how much it adds. All right, so that was about usage number 1 from my original 3 different ways to start a thread of execution. The second category, the second usage or motivation for creating a thread of execution is to start a different program as a subprocess. So back in the old days in early Unix, before they had VAX type virtual memory, as I said earlier, they would literally copy all of the memory, and the only way you could create a subprogram and run a different executable was to fork first and then have the child call exec, or one of the variants of the exec system call. So you would copy all of that memory and then throw it away and load in a new executable. So I'm showing that all of these blue things in the middle column of boxes get copied and then thrown away, and then obviously that was a bit silly. So the BSD guys came up with something that they described as a kludge. At this time, they were working, I think I have this right, at this time they were working on getting VAX-style virtual memory to work, but they still had the literal copying going on. There's quite an interesting story about how they invented mmap and so on, but there was some strange legal problems that led to them not having to change the implementation around. So that was a little bit delayed, but they also wanted to be able to start subprograms really quickly. Because if you think of it, for example, a shell script, or like a shell needs to do an awful lot of that. Every single line in a shell script is probably going to create a subprogram. So vfork was invented, and it's a very strange thing. It's very easy to shoot yourself in the foot with it, and generally normal code should never be calling it. It creates a subprocess, suspends the parent process. The child process still has the parent's memory map. So if it changes anything, including a variable on the stack, or a variable on, a global variable, or something on the heap, then the parent will see that change, which is very strange. It's almost like you're a thread, but you're still a process. But so it's very easy to completely corrupt both processes. So that's why it suspends the parent until the child either exits or exits. So either it stops running because something fails, or it loads a totally different program into memory. At that moment, the parent is allowed to continue. And that's basically a hack. It allows subprograms to be started very quickly. But you can see that it's sort of a variation on how fork works. And it's kind of an admission that the original concept of making fork super simple and not even having it, like fork has no arguments. So people finish up having to make weird variations of it because it just, they had special requirements, including going fast in this common case. So that was actually in POSIX, but then they removed it and standardized POSIX spawn. I don't see much software using POSIX spawn. Then again, most people don't have to call vfork either because people use things like system and popen, which is from libc, and you will find that they still do that inside. So POSIX has removed vfork, but you'll see that most systems still use it internally because it's very useful. They might use it to implement POSIX spawn, for example. Okay, and the third thing is creating a thread. So with POSIX, I'm showing pthread create because that's the POSIX function. With Windows, create thread is essentially the same. There's no separate process. There's no separate memory map. You're sharing almost everything. You just have a new thread of execution. Context switches between those threads may be more efficient due to the way that virtual memory hardware works, not having to be reprogrammed, TLB shootdowns and all that kind of stuff. There's no extra overhead for copies of the page table, of course, because it's the same page table. But because you're sharing global variables and file descriptors, of course, you have a whole lot of new problems in your life. You have to make sure that they don't trample each other, and you've got all kinds of new interlocking problems. And so in 2011, the C standard added a new standardized interface to the C library called threads.h. I think we can't use it yet because Apple forgot to implement it. I believe they're working on it. I've seen some clues about that. On Windows, it's been added to Visual Studio 2022, which seems to work, seems promising, but MinGW doesn't have that yet, and I don't know what to do about that, and I'm not really a Windows guy, so I'm not sure where to find out if that, hopefully that should eventually work, but I don't know when it's going to happen. One thing that I found while working on this stuff and trying to see if we could use C11 threads for Postgres, it doesn't have some things that are quite useful in POSIX, in pthreads, and one thing that jumped out at me was that it doesn't have static initializers. So when you create a mutex, you can't just give it a special value. You have to do a whole dance and initialize it with a function call and so on, which is probably, it's probably not a problem for new code, but it's slightly annoying that you can't just sort of drop it into existing code that's written with pthreads, because we use those initializers all over the place, and it's quite hard to find a place to, like a way to initialize those things. So I found that a bit odd. I just mentioned in passing, it's not really directly related to, well, it is very related to threads, but it's not directly related to, you don't need to do this to make Postgres multi-threaded, but at the same time, C11 also introduced a standard set of atomics operations. Postgres has a bunch of atomic stuff which is very similar looking, and I think that's because the C11 atomic stuff was in development and drafts had been seen, and I think it was mostly Andrus who did that work, and I think he was influenced in trying to sort of make it look roughly the same, and therefore it's not that surprising that I was able to completely replace everything with C11 atomics with a few little quirks. It works fine on all my operating systems in that I use regularly, at least 3 or 4 different systems. When we're ready to use C11, I don't have an opinion on that. There's going to be a very good talk on that shortly. We might decide to do that, but to do that, you'd really have to determine that all of the hand-rolled assembly and other magic that we've accumulated for doing that, you'd have to determine that it's not going to cause any unexpected regressions. And unfortunately, that involves poking around on a load of different architectures and operating systems and so on, and compilers. So yeah, but that's essentially orthogonal. So I just mentioned it in passing because it kind of goes with the thread stuff that came in C11. All right. I've worked on a few different projects in Postgres that made me want threads a lot. And in my earlier jobs and projects I worked on, threads were just taken for granted. I didn't realize that, it was when I started working on Postgres full time, it took some adjustment, and for many years I sort of forgot about them, and you start forgetting the arcana of working with them as well. But a couple of different projects I worked on led me to think about them a lot and start trying to find out what problems you need to solve to use them. So you don't have to read this wall of text, but this is just something I wrote on my blog in 2018 when I'd been working on parallel hash joins. To make that work, we had to come up with some way to share dynamic memory, like memory that wasn't originally allocated by the postmaster. And that involved so much machinery. I'm not that happy with it, and I know that most people who try and use the DSA system probably curse my name. It's quite difficult to use probably, but that's because it's trying to do something really tricky. It's essentially a kind of a fake software virtual memory system. Well, not quite, but it's doing address decoding and it has overheads, and it's fairly tricky. So and even when I proposed that stuff, I was already saying we've got to get rid of this. I know we haven't committed it yet, but we've got to get rid of it. And the way to get rid of it, of course, is to share the memory map. There's probably some other ways you could get rid of it, but they would also be complicated, and we discussed that at the time when that was being worked on.
Get rid of it at the same time you were proposing.
Yeah, yeah, that's what I was thinking. This thing, we've got to get rid of it. Yeah, but and more generally, the people that set out to work on adding parallel query execution to Postgres, Robert Haas and others, they made the choice not to try and make Postgres multi-threaded first. I can't speak for their motivations, but my understanding is that approximately that it's really hard and could sink the whole project, and they just wanted parallel query execution, and they could see a pathway. And that makes a lot of sense. And there certainly are other systems, other relational database systems that manage to do that. Yeah. I think it's extremely difficult for them as well. That would be my guess. I'll talk about why in a moment, actually. Okay, so another project I've done a lot of work on, I've been working on small niche parts of the AIO system, which is Andres Freund's project, which has been which is like a large piece of that is like the real subsystem itself is shipping in Postgres 18. Well, I don't want to jinx that. It's in Postgres 18 beta 1. That's a really massive and complicated project, and it adds true asynchronous I/O to Postgres. A lot more work is to be done. At the moment, it has background processes that can run your I/O operations for you, or it has I/O U-ring as a special mode that works only on Linux. But you can do native I/O on lots of other operating systems, for example, Windows. And those systems are very mature, and they're used by other databases on those operating systems that support that. So I've written patches that kind of work okay on Windows. Programming on Windows is very hard for me because I just send patches to CI and see if the tests pass. Usually they don't, and then you start again. The first port I worked on was getting it working on FreeBSD, which is my preferred hacking operating system. The relevance to threads here is that the designers of these systems didn't imagine for even a second that you would be using a multi-process design. It just clearly didn't even enter their minds. They don't even tell you in the documentation that it doesn't work. It's so obvious. I guess. Like, who would do that, right? What I'm describing is one process starts an I/O, like starts reading a chunk of data off disk into memory, and then it goes away and does something else. I don't know, maybe it's waiting for a lock somewhere. Some other process comes along and wants to access a buffer, and that buffer is associated with that I/O that's running, and in fact, it's already completed. It can't wait for that first process to consume the completion event from the kernel and terminate the I/O and like update all the buffer headers and so on and make the buffer valid, because you might deadlock. Just the way the levels of locking and so on work here, asynchronous I/O generally, to be deadlock free, and even just to be performant, it needs to be able to complete any I/O that it can get its hands on from any backend, right? And you can't do that directly using the Windows AIO interfaces, or the POSIX ones that are used on FreeBSD and a bunch of other operating systems. So I did manage to make it work. It was really not pretty. And it really made me think, should I propose these patches, or should I just go and work on threading first? And yeah, I still don't know the answer to that question. I'll write about that on the mailing list soon. All right. There's a whole lot of other places where you can see that operating system designers didn't even contemplate that you would want to do something cross-process. For example, Windows has futexes, but they don't work cross-process. There's a bunch of IPC-like things, semaphores and so on, that don't work cross-process on a number of operating systems. Mac OS is an example that I happen to have right in front of me, like this computer. It would be really easy for them to make that work. I know how you do that. It's very easy. Like, it's just a matter of some address mapping stuff that's not even complicated. But they didn't do it, which just shows that no one wants it, which is really interesting to me, that we're struggling with things that other people just don't do that, right? I thought that was kind of interesting. In theory, Postgres could use, even with a multi-process model that we have today. I've hacked up prototypes of this before, and it works fine. You can delete half of our LWLog stuff and replace it with pthread mutexes, for example, even though you're using processes. And you should get pretty good performance, you would think. I don't know, that maybe not, but we have a linked list of semaphores that we go and poke. So, if you get the kernel to manage the wait lists, probably it can do a better job. I don't know, but we couldn't consider that because it doesn't work cross-process on some systems, and POSIX allows for that. It's probably closely related to these things are all kind of related, right? So stepping right back and moving to the second part of the talk, let's talk about how you would arrange the threads of execution in general in a database. For this, I wanted to get some terminology and get some kind of overview of what other databases are doing. This is actually a fairly old paper, 2007. Look, that name's Stonebreaker again. Anyway, so it's pretty old, and the things that it says about other databases are probably out of date by now, but they still give some idea, and the things they say about us are not out of date. So the process model that we use today is fairly straightforward. For each socket coming into Postgres, there's a process running, and then that process manages the state for a session. And there could be many of those. You might have 1,000 sockets, then each one's got a process, each one's got a session, and the operating system does all CPU multiplexing. So maybe you've got a 2-core system. Let's pretend it's a very small computer, and it's up to the operating system to figure out how to run your 1,000 backends, if they're all runnable right now. And so there's a whole lot of context switching, perhaps, between those processes. So here's a little quote from that paper. I just, like a scrapbook, cut out the little descriptions from that paper. This is, or at least was in 2007, Oracle's full process model. We get a name drop here. Postgres runs the process per DBMS model worker exclusively on all supported operating systems. So the simplest change you could make, I think, and I think the most realistic design we could consider, is to keep everything the same as now to the maximum extent possible, but just use threads. So, and I'll say what I'm excluding on a later slide. Like, the idea is to try and make everything just the same shape and then find all the things that break and fix those. So you've still got one thread for each socket coming in, and that's associated with the session. You're still letting the operating system map all those threads onto only 2 hardware cores, so it does all the context switching between them. Context switching between those threads is probably cheaper than context switching between processes. It says here that DB2 defaulted to that model in 2007 at least. MySQL uses that model. It's fairly straightforward, and I think it's probably a lot more efficient than what we're doing now. And many people have tried this. I've become aware of a lot of different prototypes and people who've written about trying to get this working. I think it's kind of the most obvious path forwards. There's another idea, just for completeness in the paper, it talks about another idea which I have never even considered. It's kind of madness, but in some systems, they had ways of doing multiplexing between, you could call them green threads. This idea is basically dead in C. There are a bunch of other languages that do this, and with great results. They might have these kind of green threads, or whatever you want to call them. Windows has fibers. I think the idea has basically gone out of fashion in Windows as well. For native code, should we say. But some other languages do this stuff. It just doesn't make that much sense for C. And in particular, the stuff you need to do that, so POSIX used to have these calls, get context, set context. You could basically photocopy your stack and all your registers, and you need to be able to do that so you can switch between threads of execution. You could also do it in a whole lot of horrible, non-portable ways that are very architecture and operating system independent. We certainly wouldn't want to do that. So that whole concept is not really doable. So I'm just mentioning that for completeness, since the paper calls that one of the obvious ideas. So there's a kind of a holy grail. It's my understanding that this is approximately the state of the art for this type of thing. This involves about 4 different boil the ocean projects coming together, and I'm not even seriously considering it, right? But the ideal system would have 1 thread running per hardware core, keep them busy as much as possible. You've got your own scheduler, which has got work queues, and you've got all of your I/O is asynchronous, so it's driven by events coming in, and your message comes in on a socket and is actually the completion of a read that you started earlier. Queue up a little work task. But first you need to take your whole executor and smash it into pieces and be able to run those small pieces on your scheduler. So that's just a whole, you absolutely cannot start with that in mind. But it might have, the reason I mention it though, is that well, firstly it says here that a number of other systems do use that design. SQL Server defaults to that model. Almost everyone uses that model. It's probably the most efficient model. I think Sybase does the same. Probably many other systems do the same. And certainly a lot of HPC systems that aren't databases in general use this type of approach, and runtimes for other languages. All right, so the reason I mentioned that is because one of the most basic and obvious problems when Postgres becomes multi-threaded is that it's totally loaded up with global variables, just millions of them. And they represent current transaction state, current session state, they represent gooks and all sorts of transient things. I think I'm aware of more than half a dozen people who've tried to just turn them all into thread local variables, which basically works, right? It makes them behave as though they're with the same syntax. It basically means that you continue to treat everything basically the same way. And what Heikki has been doing in his branch, which he's shared publicly and which he talked about at this conference, I actually can't remember, sorry, in the European conference. He talked about his branch, which is public, and I'm referring to a few things in his branch here. Instead of just going and directly marking everything thread local, he's got a classification scheme where he goes through and annotates what different variables are for, which I think is a very good idea. And really, they just turn into thread locals. But in future, there could be some different schemes. Another idea would be to take all that stuff and stuff it into objects and then pass pointers to those objects around. And you would then need to add a lot of extra arguments to a lot of different functions. I think it would be really complicated. But it is probably what you need to do to get to that holy grail design. And not just session, but also transaction and some other objects. Actually, this is code that's actually in master because I thought about that a lot when I was doing some parallel query work, and I was like, essentially like, hey, guys, we should have a session struct. And here's one thing I need to solve my current problem. And I was kind of imagining that we might start to put other things in there, but I kind of came to understand that it's probably not so easy, and it's probably better not to make unnecessary changes and try to make the patch set digestible. And I think it's a reasonable place to start, just to use thread locals everywhere. And later on, we might eventually come around to something like that. Okay, so here's a list of people I know of who've tried to do thread local based thing with various success. CMU Peloton project, they also changed it all to C++, pretty impressive. Postgres Pro had a working prototype that they proposed to the list, and no one was really that interested at the time, which is kind of a shame. But there were multiple early attempts to port Postgres to Windows using threads, and they were able to run to some degree. I found a guy on Reddit who spent some time getting Postgres to work like this, and then talked about it on Reddit, and then read our wiki, which said we don't want this in our features we don't want. That's been deleted now, but that was a thing we had on the features we don't want. So yeah, this is the reason that it was on the features we don't want thing is it's been discussed many times. People have tried this many times, including myself. Heiki's got a pretty cool branch that I think, yeah, there's a number of people now who really do want this, and I think, yeah, there's a chance it could really happen this time around. Fingers crossed. Another little architectural choice you might want to think about is whether, like, in a multi-process mode, you've got the postmaster and all the child processes. How does that look? Do you still need a postmaster? I think you do. You certainly do if you're going to have a multi-process and a multi-thread mode with a switch, which I think we should do, because otherwise too many things will break in the first version. Many people have said, well, why can't you just use systemd or something like that? Well, one problem is that of the 11 operating systems we target, almost all of them are not Linux. Also, not even all Linux systems use systemd, and I think there might be some extra reasons to do with state management. So, but the fact that we probably want to have both multi-process and multi-thread mode in the first hypothetical first version of this means that you probably just want to have a postmaster anyway. I don't know. Maybe it should be renamed to supervisor because it wouldn't do much anymore. Like it would mostly just be restarting the thing if it crashes, because all of the logic to, excuse me, start new threads and so on would just be in the main container process. But it still needs to exist because if that process crashes, it needs to coordinate restarting it and letting recovery run and so on. So I'm going to talk about some work in progress, actual concrete stuff. So you can look at Heiki's branch. It's got some code which has come from various places. It's getting rebased from master, of course, and I think Stas Kelvich seems to be helping him with some of that stuff. A number of pieces that you need to make that work have just been done independently in master and are still being discussed, and it will be in the next commit fest, and they flow into that branch. So, but yeah, you can try it out and run it, and probably crash pretty soon. But you can run some queries, and you can get some stuff working, and you can see the basic idea, and maybe even help. So yeah, really general goals. We almost certainly want to run both multi-process and multi-threaded modes, especially because there's a whole ecosystem of extensions, and it'll take a long time for all the kinks to be ironed out and for people to understand the new program, and also just generally for the whole thing to be stabilized and debugged, right? And for all of the performance implications to be fully understood and so on. So we want a switch that makes it exactly like it is now. So yeah, the flip side, there's a whole bunch of non-goals for the prototype work. So each backend is a thread now. And so they're in the process, and they could see each other's file descriptors. The file descriptors they opened, there's just one set of file descriptors for a process. But trying to share them between backends, that's a whole project that you don't need to deal with to make this work. And as we all know, the more crazy projects you tie together with string, the more likely that the whole thing collapses and doesn't work. It's the same with the memory used by relcache, syscache, and various other things. One of the famous ways to make your system run out of memory is to have many backends with a lot of cache data. We don't really even do cache invalidation for most of these caches, and it's duplicated in every backend. So many people have wanted to share that stuff, but cache invalidation is one of the famously hard things, and that's all tied up with. That's complicated. Again, let's not try and do that. Let's just let each backend waste a whole lot of memory by duplicating that stuff, so that multi-thread mode and multi-process mode are almost exactly the same in their behavior. There's a whole range of possibilities with memory contexts. Again, keep it simple, make them work as if they were processes. Don't share any memory context between backends. The whole DSM, DSA thing, although I would like to see it go, it's better to just leave it all as it is, and then later on that could eventually, maybe you can't even do that until the multi-process mode eventually goes away, which would have to be the goal, right, I think. The idea of having both multi-process and multi-threaded is to allow a multi-year transition for the ecosystem. And some other non-goals there, which are, I guess, self-explanatory. So some concrete work-in-progress stuff. How should we even talk to threads? How should we talk to the operating system? My current idea is that it's a little too soon to use C11, mainly because of macOS. But I don't want to make up new names for things. I like the C11 names. I like to imagine that in the future, eventually, this runs everywhere, and we do just use C11. So I proposed PG threads.h to be like threads.h from the C standard, but with PG prefixes everywhere. I did have a patch in the last cycle, which had a few problems. I've got a better version I'll propose again soon. It actually works out to be a net zero patch, and it deletes as many lines as it adds, because we have many little things like that all over the place, and some of them have bugs, and they're inconsistent, and so on. So it's a kind of a code cleanup thing as well. But people don't have to agree with my idea of using the C11 names. I don't know. Some people prefer to use the POSIX names and then try and make Windows look like POSIX. I don't like that, because it never really will work exactly like POSIX, so why even pretend? Why not just make a new set of names that work in a certain way, and we define what the set of things we want to use is, and we can deal with the differences. That's kind of my approach. Over the last, certainly in this release, but probably, I'm almost out of time here. There's been a whole lot of work done by many different people to remove all kinds of non-multi-thread safe code all over the place, and that's really cool. It's great to see that happening. If anyone, there's plenty of space for anyone who's interested in this stuff to go looking for those kinds of things, particularly to do with locales. We kicked out a lot of global locale usage. It's not finished yet. There's a whole lot of places where we have static buffers and so on. So that's little pieces that can be done just in master without having to get involved in Heiki's public branch. A major piece of work here, and which is proposed last cycle, I think it became a bit too complicated and we kind of ran out of time, is to chase down all the places where Postgres uses signals and get rid of them, because they assume essentially, and I mean signals to communicate with a backend. Obviously, you can't use signals to communicate with a backend if the backend is no longer a process. Maybe you could use pthread kill, but yeah, it doesn't really seem to make much sense. And in fact, while studying that, it became very clear to me that our system has become, over the years, has become a cooperative system. And therefore, latches should probably be the basis for almost all wake-ups in the system. And that technology works pretty well. I proposed that, and then Heiki, who was the original inventor of the latch system, he said, why don't we also get rid of latches? And he did some further refactoring work. And so the current proposal, it creates this new thing called an interrupt and gives it a meaning and makes it into backend and so on. And we figured out how to do that in a way that lets us get rid of a whole lot of use of signals. There's some stuff on the wiki. I plan to try and update it some more and try and keep it up to date with what's happening. But try to survey stuff like where are all the places we fire signals all over the place? How do we kill that one? And the answer is generally somehow it's got to be latches or rather interrupts. And that work is ongoing. There'll be new versions of that patch sets in this cycle. That's the end of my talk. I just wanted to say that it's really a complicated, big project, and it's going to take a lot of people, a lot of effort to try and get something that is stable and sustainable and works for the ecosystem. But I think we have to do it. I don't think we can go on running as a multi-process system. That's the end of my talk, and I think there might even be a few seconds for questions. All right.